Hi everyone, this is Physics 2 Lab for Magnetic Braking with Faraday. I'm Xining. The goal of this lab is to observe the falling time of a bar magnet through a conductive tube and compare this time with the time generated by the computational model using Python. Here are the preview results of this lab. For the observed model, the average falling time is 0.841 seconds, while the computational model is 0.639 seconds. Here are the key physics concepts. The Faraday's law and the Lenz's law tells that a changing magnetic field induces an electromotive force M, while Lenz's law specifies that the induced current flows in a direction that opposes the change causing it. The following are the formulas, where the non-Coulomb electric field is the result of changing magnetic flux, and dl represents the total parameter through which the induced current occurs. The negative sign before phi dt implies that nature abhors the changing magnetic flux. If the direction of the magnetic field and the area are perpendicular, then the magnetic flux can be simplified as B times A, and the magnetic flux we're using in this lab is shown here. The magnetic field of a current Y is provided here, while theta is the angle between the magnetic field and the current. The system is the bar magnet, and the surroundings are the conductive foil and the earth. There are two forces on the magnet, Fg and Fb. Fb points upward since Fb by the bar magnet on the foil is increasing downwards while the magnet falls. Thus, by Lenz's law, the Fb on the bar magnet points up. Here are the properties of the foil and the bar magnet. The average falling time is 0.841 seconds. The initial properties are here. The two functions to calculate the magnetic field by the bar for the bar magnet is in the middle, and I use the formula in lab 2. The derivative of the magnetic flux is at the bottom, while I use the formula on the right. The Fg on the bar magnet is defined here, and the induced current on the wire is defined using Ohm's law. On the right, I define the Fb by the bar magnet on the ring using the magnetic field function created in the previous slide, and then I got the sine theta between the magnetic field and the mu magnet. Since n head of the ring and mu magnet are both along the y-axis, I can still use the angle theta for the Fb calculation by the ring current. So by applying Newton's third law, I can get the magnitude of the Fb force by the ring current on the bar magnet. Thus, the forces on the bar magnet are Fg by the earth and Fb by the ring current. The result shows that it takes 0.639 seconds for the bar magnet to fall in the tube. The result of the computational model is slightly smaller than the observed model. This could be caused by not taking the air resistance into calculation, or the magnet touches the tube while falling, creating inaccurate Fb calculation. Also, the time measurement could be inaccurate. What if there's close to zero resistivity of the conductor? The falling time of the bar magnet will be longer. Remember, we used the Ohm's law to calculate the induced current on the wire, so R in the denominator will be smaller, causing I to be bigger, thus causing Fb provided by the current to be bigger. So for F net on the bar magnet, the upper force Fb will be bigger than before, causing the magnet to fall slower. What if there are holes in the tube? Then the bar magnet will fall faster, since at certain times where the bar magnet passes through the tube, there's no upward Fb, thus it will fall faster. That's the end of the presentation. Thank you for listening.